Computers don't like doing subtraction directly. Instead, they use a small trick called complements to turn subtraction into addition, which is much more easier for them because of their hardware alignment. There are two main types of complement: R's complement and R-1 complements. The name depends on the number system. In binary, which is up base 2, we use 2's complement as R is equal to 2, and 2 minus 1, 2's complement. And when I substitute 2 for this R, I will get 1's complement. And decimal, which is of base 10, we use 10 complements as you replace 10 for this R, so I will get 10's complement. And when 10 is substituted for this R minus 1, so it will be 10 minus 1, that will be 9's complement. A complement is just another way of representing a number so that subtraction become easier. In this video, we will only focus on R's complement. So we have the question that what is R's complement? Given a positive number n and base R with n integer part of n digits that is represented by small n, the R's complement of this n will be represented R. The R complements of a number is found using this idea of take base R raise it to the number of digit n, then subtract the number. So and this will be for n is not equal to 0, and R raised to a power n minus capital N is 0 when n is equal to 0. Now we will solve some examples that will help to clarify this definition. Alright, so here we will have to find 10's complement of 52,520 or 52520 to base 10. So as we do need this positive number, so given positive number which is this 52520 and base of the number system that is represented with R, it is 10. The number of digits in the integer part of this n, so we will count these integers. So this whole, there is no fraction, all of this is integer. So 1 2 3 4 5. Now let's substitute these values in this idea that is R raised to power n minus capital N. So for R I will substitute this 10 raised to a power of n, which is this 5 minus n, which is this number. So 52520, and using calculator I will come up with 5. 10 raised to a power 5 will give me 1 0 0 0 and this 0 minus 52520. So using calculator I will come up with 47,480 is the complement of this number. So bear in mind, or I will note this one in later stages, and then we will deduce something important from this. Now moving on to the next example. Now this is example number 2, and we have been asked to find 10's complement of 0.3267 to base 10 or decimal fraction. Here this given positive number which is represented by n is 0.3267 and base of number system that is represented with R, it is 10, and number of digits and integer part of this n. So we don't have integer part involved, which is 0 integer part, and the fraction part has some digits. So we don't have number of digits and integer part, so this will be 0. Right now I will substitute these values into this R raised to a power small n minus capital N. So we have R that is 10 having power 0 minus 0.3267. So 10 having power 0 is equal to 1 minus 0.3267, and by using calculator I will come up with 0.6733. This is the complement of this number. Alright, now bear in mind as I will use these answer and will deduce something important, so stay in the video. Now this example number 3, we have been asked to find 10's complement of 26.639 to base 10 on decimal number. So the given positive number which is represented by n is 26.639. Number of base of number number system which is represented by R is 10. It is a decimal. Now number of digits and integer part of this n, that is we have 26. So 1, 2. We have number of digits and this integer part is 2. Well, 0.639 is the fraction part of this n. We only need to have digits and integer part. Now I will substitute these values into this. That will leave me with 10. R is 10 having a power of 2 minus capital N, that is 26.639. 10 square is equal to 100 minus 26.639, and by using calculator this is equal to 73.361. So this number 26.639 has a 10th complement of 73.361. Now let's move on to some binary numbers. So here we have been asked to find 2's complement using R's complement of 101100 of this binary number. So the given positive number which is represented with this capital N is 101100. Base of number system which is represented with R is 2, and then number of digits and integer part of this N is 1, 2, 3, 4, 5, 6. So now I will substitute these values into this idea. So I will get 2 raised to power N, which is 6, minus this number 101100. So 2 raised to power 6 is equal to 64. But remember that we have this n decimal number and this number is binary 101100, which is of base 2. Here we got situation where we have decimal unit and binary subtrahend. To execute this subtraction operation, unit and subtrahend must be of same base. We can convert both, but in this case I will convert this decimal unit into binary. To do so, let me take it as rough space. I will divide this by 2 as I have to convert it to binary, so this will be divided by 2. So this is the quotient and here I will write remainder. So when 64 is divided by 2, I will get 32, remainder will be 0. When 32 is divided by 2, I will get 16, remainder will be 0. 16 divided by 2 will give me 8, remainder is 0. 8 divided by 2 will give me 4, remainder is 0. 4 divided by 2 will give me 2 with a remainder of 0. Now 2 divided by 2 will give me 1 with a remainder of 0, and 1 divided by 2, so I will get a quotient of 0 and a remainder of 1. So this decimal 64 is equal to 1 followed by 6 zeros and binary 1 0 0 0 0 0 0 minus 1 0 1 1 0 0. To execute this binary subtraction, I will write this unit and subtrahend both vertically, which is more easier for me. 1 0 0 0 0 0. Now this 0 0 1 1 0 1. When 0 is subtracted from 0, I will get 0, again 0. Now when 1 is subtracted from 0, it can't be done. That is why I have to go to the next higher bit and take a borrow. So here I have 0, so I can't make any borrow from here. That is why I will look in next column, then in next column. So all the way along I am getting 0, but here I will get 1. I have made a full tutorial on this subtraction where I have explained each and every one terms that will make this subtraction easier for you. So by carrying this 1 will become 2 in this column, and now when I take 1 from this 2, it will become 1, and this taking 1 from this column will become 2 in this column, and now I will take 1 borrow from this column to this column, so this one will become 1 and this one will become 2, and the same process will keep on going as I take 1 borrow from this, so it will be remain 1 and this one will be 2. Now 2 minus 1 will give me 1, and 1 minus 1 will give me 0, 1 minus 0 will give me 1, and 1 minus 1 will give me 0. So we come to know that this is equal to 0, 1, 0, 1, 0, 0. I would like to encourage you to watch this binary subtractions full lecture on hybrid OR. Now let's move on to next example. In this example number 5, we have to find 2's complement using OR's complement of 0.0110 of this binary number. So the given number, which is represented with capital N, is 0.0110, and base of this number is 2, which is represented with R, and number of digits in this binary number, we don't have any integer part, we have only fraction digits, so we will write it as 0. Now substituting these numerical values into this, so R has a value of 2, N has a value of 0, minus 0.0110. Anything having power of 0 is equal to 1, minus 0.0110. Remember that this is a binary number, so I will also consider this one as binary, writing it in vertical form, which make it much more easier to solve. So 1 point and we have 0.0110, so 0, 0, 0, 0. These minute and subtrahend both are in binary, so 0 subtracted from 0 will give us 0. But now we have to look at this, that when 1 is subtracted from 0, that can't be done. That is why I have to go to next higher bit column, and here I will find 0. So for borrow, I will go to next higher bit column, so again I am finding 0, so I will go for next higher bit column, that is 1. So when 1 is borrowed from this column, it will become 0, but borrowing 1 from this column to this column will give me 2, and this least a lower bit column, and then I will borrow 1 from this 2 to this column. So when 1 is borrowed from this, it will become 1, and borrowing 1 from this column to this will give me 2 in this column. And similarly, when I borrow 1 from this column, this one will be left with 1, and this 1 will become 2 in this column. Now 2 minus 1 will give me 1, and I have 1 in this column, so 1 minus 1 will give me 0, and 1 minus 0 will give me 1. 0 minus 0 will give me 0. So this is equal to 0.1010. Now let me combine all these questions which I solved over here. I have solved 5 example, and let me gather its data. What I mean by this is like this number has a complement of this, so let me write it as we have solved for 5 examples. First 3 one was base 10, or that were decimal numbers, and from this definition and the example, it is clear that 10's complement of a decimal number can be found by leaving all the least significant zeros unchanged, as we have 0 over here, so it will be unchanged. Subtracting the first non-zero least significant digits from 10, and when this number is subtracted from 10, it will give us 8, and then subtracting all the higher significant digits from 9. So I repeat, you need to know that you have to leave the least significant zeros unchanged, subtracting the first non-zero digit from 10, and then all the higher significant digits must be subtracted from 9. So look at here, we don't have 0 over here, so the first digit will be subtracted from 10. So when 7 is subtracted from 10, I will get 3, and then 6, all the higher significant figures will be subtracted from 9. When 6 is subtracted from 9, I will get 3, and when 2 is subtracted from 9, I will get 7, and when 3 is subtracted from 9, I will get 6. Similarly for here, this is the least significant, or the first non-zero least significant digit, so it will be subtracted from 10, I will get 1, and then subtracting all the higher significant digits from 9. So when 3 is subtracted from 9, I get 6. When 6 is subtracted from 9, I will get 3, and when this 6 again is subtracted from 9, I will get 3. And when 2 is subtracted from 9, I will get 7. Now, let me try. If I have to find tens complement of this number, so it will be like we don't have least significant 0. So this 8 is subtracted from 10, I will get 2. And now these higher significant digits will be subtracted from 9. So when 7 is subtracted from 9, I will get 2. 3 subtracted from 9, I will get 6. And when 4 is subtracted from 9, I will get 5. So this is the R complements of this number. And you can also verify this just by solving as I have solved this example. Now the 2's complements can be found by leaving all the significant 0 in the first non-zero digit unchanged and then replace zeros with 1 and 1 with zeros. Now look at this. This is the zeros and this is the first non-zero digit. So we will have to leave it as unchanged. You can see. Okay. So leaving these unchanged as here and then replace every one with 0 and 0 with 1. So I have got 1. So I will turn it into 0. I have 0 over here. So flip it into 1. So I have 1 and flip it to 0. So look at here. This is the least significant 0. So and this is the first non-zero digit. So leaving it as it is. So I have leave it and then turning this one into 0. So I have got 0 and then 0 is replaced with 1. So what if we have to find R's complement of this number? So as I told you that you have to leave the all significant in the first non-zero digit unchanged. So leaving these 3 unchanged and then flipping all the ones into zeros and zeros into 1. So I will get this one 0. This 0 will be turned into 1. This 1 will be turned into 0. For this 0 I will write 1 and this 1 will be turned into 0. So you can verify these just by substituting these values as I have solved over here. So here I am writing these rules just to make it easy and also easy to remember. So for tens complements we have to keep zeros at end, subtract first non-zero digit from 10 and then subtracting remaining digits from 9. Like to using R's complement, I have to find tens complement of 8922 having some zeros. So what they say about 0 that we have to keep the 0 at the end, and now this is the first non-zero digit. So we have to subtract first non-zero digit from 10. So I will get 8 and then the remaining will be subtracted from 9. So when 2 is subtracted from 9, I will get 7. When 9 is subtracted from 9, I will get 0. And when 8 is subtracted from 9, I will get 1. So this is the 10 complement for this number. Now for 2's complement, we have to keep trailing zeros and first one unchanged. Like we have a number, let be 1 1 0 1 1 0 1 0 0. So what they say that we have to keep the trailing 0 and first one unchanged. So this one will be unchanged, zeros and first non-zero digit. And then what? Flip all remaining bits and then I have to flip also. This 0 will become 1, 1 will be 0, then this 1 will be 0, this 0 will become 1 and these ones will be turned into 0 and 0. So this is the 2 complements for this binary number. And about this one they say they flip all bits. So remember this one, that flip all bits. So what they say that first I will flip all of these numbers. So every one will be turned into 0 1 0 0 1 0 1 and 1. So I have flipped all of these bits. Now I have to add 1. So by adding 1, so when 1 is added with 1, this is a binary, so I will get 0 and 1 will be carry, and now 1 plus 1 will also give me 0 and 1 will be carry, and now 1 plus 0 will also give me 1, and now 1 0 will give me 1 0 0 1 0 0. Now look at this one, they are identical. This number and this number, it is same. So this is the shortcut and very important rules for these complements. Alright, so this is how you can find the R's complement of a number, and this complement exists for any base or may be obtained from the definition as I have explained. So the example listed here use number tens and 2 because these are the two bases of most interest to us. The name of complement is related to the base of the number. For example, this r minus 1 is a nines complement for decimal and it's ones complement for base 2. So it definitely depends on this base number. In next lecture, we will cover r minus 1 complement. So see you there. And if you have any question regarding this topic, you can ask in the comment section. Thank you.